Welcome to this video on digital electronics. In this video, we will be discussing on number systems. The four important number systems: decimal, binary, hexadecimal and octal numbers. And we will also look into conversion from one number system to another number system. First, let us consider decimal numbers, which we are all very familiar with since we have used decimal numbers right from childhood. Decimal number has 10 digits ranging from 0 to 9, and it is represented to the suffix 10, and even if suffix 10 does not appear, by default it is a decimal number. The base or radix is 10, and decimal numbers are weighted numbers. That is, the value of a digit is determined by the position of the digit in the number. The example of 5672, digit 5 has a weight of 1000, and the digit 2, which is in the units place, has a weight of 1. 7, which is in the tens place, has a weight of 10. So, moving from right to left, the weights of each of the digits are multiplied by 10 power 0, 10 power 1, 10 power 2, 10 power 3 and so on. Considering the second example, which is a fractional number 472.53, for the integer part, each of the digit is multiplied by the weight, which is 10 power 0, 10 power 1, 10 power 2, moving from right to left for each of the digit. And for the fractional part, after the decimal point, the weights for each of the digits are 10 power minus 1, 10 power minus 2 and so on. This gives the general representation of a decimal number. The leftmost digit indicates the most significant digit, MSD, because the weightage of this digit is the maximum for that particular number, and the rightmost digit gives the LSD or the least significant digit, whose weightage is the minimum. And the number can be expanded by multiplying each of the digits by their weights, starting from 10 power 0 to 10 power 1 and so on for the integer part from right to left, and multiplying by 10 power minus 1, 10 power minus 2, etc., moving from left to right for the fractional part. Problems have been given in the pink color box. Pause the video and solve the problem. Similar problems appear in the video in the further parts. So, whenever a pink color box with problems appear, pause the video, solve the problem. The solution will appear in the blue color box. Again pause the video, check your answers, verify them and then proceed with the video. Next, moving on to binary numbers. Binary means by 2. So, binary number system has two digits, 0 and 1. The base or the radix is 2. It is also a weighted number, and the weight of each bit depends on the position in the number. Example of 1011.101 to the base 2. The weights of the numbers here are based on power of 2. So, the first digit, considering the integer part, the first digit has a weight of 2 power 0, the next 2 power 1, moving from right to left. And moving from left to right for the fractional part, the weights are 2 power minus 1, 2 power minus 2 and so on. And expanding this and summing up, we get the decimal equivalent of the binary number. The left side table shows the decimal number and binary representation for these decimal numbers. So, first let us look into counting in decimal number. Starting from 0, we move on 0, 1, 2, 3, so on up to 9. When we have exhausted all the decimal numbers, we consider the next digit position. So, the next number after 9 is 10, then 11, 12, so on up to 99. When we have exhausted all the digits for the two positions, we take up the next digit position. So, 100, 100, then 101, so on. Counting similarly in binary, we have first 0, then 1 for since binary number has two digits, 0 and 1, which are already exhausted, we consider the next digit or the next bit position, and we have 10, then 11. Now, both the bit positions are exhausted, and therefore, the next bit position 100 is for 4. So, proceeding so forth, we can go for binary counting. 4 bits in a binary number is called a nibble, and 8 bits make a byte. So, 8 bits in a binary number, which is a byte, is commonly used in computers. Pause the video, solve the problems. Pause the video again, verify the answers and then proceed. So this is a general representation of a binary number. The leftmost bit is called the most significant bit and the rightmost bit is called the least significant bit. And expanding with 2 to the powers, we can get the decimal equivalent of the number. So with 8 bits, we can represent 2 power 8, that is 256 numbers ranging from 0 to 255. And with n bits, we can represent 2 power n numbers ranging from 0 to 2 power n minus 1. Moving on to octal numbers. Octa means 8. So it has 8 digits ranging from 0 to 7. The base or radix is 8 and it is also a weighted number. And the position or the weights of each of the position is to the power 8. 5362 to the base 8. Each of the digits are multiplied by the power of 8. 8 power 0, 8 power 1, etc. moving from right to left, similar to the examples that we have seen in decimal and binary. Pause the video, solve the problem given in the pink color box. Pause the video again, check the answer and then proceed. Next, hexadecimal numbers. Hexa means 16. So it has 16 digits starting from 0 to 9 and then the alphabets from A to F are used. So hexadecimal number has 16 digits represented from 0 to 9 and A to F. It is base 16 and it is also a weighted number system with weights being 16 to the power. The example of 3FD to the base 16, D is multiplied by 16 power 0, F by 16 power 1 and 3 by 16 power 2. The decimal equivalent of D is 13 and F is 15. So solving that, we get the decimal equivalent of the hexadecimal number. Answer the problem that is mentioned in the pink box. Pause the video again, check your answers and proceed. This table gives the decimal, binary, octal and hexadecimal equivalent of the numbers. Decimal 0 is represented as 0000 in binary. Actually, it can be represented by a single 0, but since in this table we have shown a maximum of decimal 15, which is equivalent to 4 ones in binary, that is 1111, we have used 4 bits to represent all the digits and similarly 2 bits for octal numbers. So decimal 0 is 0 in binary, 0 in octal and hexadecimal it's 0. Proceeding similarly, 8 in decimal is 100 in binary. 7 in decimal is equal to 7 in octal. Next 8, since all the 7 digits are exhausted, we go to the next digit position and so octal 8 is 10 and hexadecimal is same 8. Proceeding so forth up to 15, decimal 15 equivalent is given. Now, can you give the equivalent for decimal 16? In binary, all the 4 bit positions are used. So, the next bit position has to be used. So, equivalent for 16 will be 10000, that is 1 followed by 4 zeros, and octal will be 20, and hexadecimal, since all the digits are exhausted, the next bit position or next digit position has to be used, that is 10. So, decimal 16, the equivalent hexadecimal is 10. So, any base or radix R, a number, will have R set of characters ranging from 0 to R minus 1, as we have seen in the 4 previous cases. Binary has 2 characters 0 to 1 and similarly base 4 system has 4 characters ranging from 0 to 3 and base 7 has 7 characters from 0 to 6. Now pause the video, solve the problem, check your answers. Why is subdivision 5 invalid number? Because it is 58.36 to the base 8. Base 8, the valid numbers are 0 to 7. 58, 8 is an invalid octal number. Similarly, in the next example, 2764 to the base 7. Base is 7, valid numbers are from 0 to 6. So, 27, the 7 is not a valid number or not a valid digit. So, we have seen the 4 number systems: decimal, binary, hexadecimal and octal. Now, we will look into converting from any radix to decimal number. As we have seen in the previous slides, converting would be multiplying each of the digits by the radix to a power, suitable power based on the position of the digit. So, for the integer part, it is multiplying by r power 0, r power 1, r power 2, moving from right to left. And for the fractional part, it is multiplying by r power -1, r power -2, moving from left to right. Now, pause the video, solve the problems. Pause the video again, check the answers, proceed. Let us look into converting any decimal number to any radix. So, this involves 2 parts. One is conversion of the integer part and another conversion of the fractional part. For the integer part, successive division method is used, and for the fractional part, successive multiplication is used. First, we will look into conversion of the integer part from decimal to any radix. So, we use successive division method. So, first the integer part is taken and divided by the radix or base to which it should be converted, and then the remainder is stored. Next, the quotient is taken and again divided and the remainder is returned. This is proceeded till the number cannot be divided by the radix any longer. So, take the example of 42 to the power 10 to convert to binary. So, the radix is 2, therefore, 42 divided by 2 gives 21, the remainder is 0, which is written separately. Then 21 divided by 2 again, the 10, and the remainder is 1, which is written separately. Proceed so far till we get a 1. So, 1 cannot be divided by 2, so stop over there. So, write the answer in the reverse order. So, 1 0 1 0 1 0 to the base 2 is the solution. Next, the example of the same 42 to the base 10 to octal. So, 42 octal, the radix is 8 divided by 8, 8 5 is a 40, remainder is 2, which is written separately. Now, 5 is a quotient. This cannot be divided by 8, so stop over here. So, write this in the reverse order, the remainder 52 to the base 8 is the equivalent of, or octal equivalent of, decimal 42. Now, pause the video, proceed with the problem. Pause the video again, check your answer, go ahead. So, we have seen converting the integer part of a decimal number to any radix. Now, converting a fractional part of a decimal number to any radix, successive multiplication method is used. In this method, first take the fractional part multiplied by the radix or base. Note down the integer value separately of this solution, and then from the solution take the fractional part, multiply it again by the radix and note down the integer part, and repeat this step over and over again till the fractional part becomes 0 or sufficient number of digits is obtained. Then read downwards to get the solution. So, example of 0.125 to the base 10 to binary, binary is 2. So, 0.125 is multiplied by 2, we get 0.25. The integer part is 0, noted down separately. 0.25 into 2, 0.5, again integer part is 0, noted. 0.5 into 2 is 1, so integer part 1 noted down here, and the resultant fractional part is 0. So, the multiplication can be stopped here. Now, read the answer downwards. So, 0.001 to the base 2, that is the solution. So, converting any decimal to radix, the decimal number is given. Consider the integer part separately and the fractional part separately. The integer part, proceed with successive division method to get the result, and for the fractional part, proceed with successive multiplication method to get the solution. Pause the video, solve the problems. Pause the video again, check your answers and then proceed. So far we have seen conversion from any radix or any base to decimal, where each digit position is multiplied by the radix to the power based on the bit position, and we get the solution. And similarly, we have also seen conversion from decimal to any radix. In this case, the integer and the fractional part have to be considered separately, and successive division method is to be used for the integer part and successive multiplication method for the fractional part. If any number has to be converted to any other radix, suppose radix R1 has to be converted to radix R2, then radix R1 should be converted to decimal, and then the decimal number should be converted to radix R2. There is a shortcut method for conversion for binary, octal and hexadecimal. Let us have a look at it. To convert from binary to octal, first we know octal numbers range from 0 to 7, and the maximum value 7 can be represented using 3 binary bits 1 1 1. So, given a binary number, now for the integer part, group 3 bits together from right to left, and if any digit does not have sufficient number of bits, pad it with 0. For the fractional part, group 3 bits together starting from left to right, and if the last digit does not have sufficient 3 bits, pad it with zeros. Now convert these 3-bit numbers into octal numbers and we have the result, very easy. Now converting octal to binary is very simple. Take each octal digit and represent it by the binary equivalent using 3 bits, and that is the binary solution. Next, considering binary to hexadecimal. Hexadecimal, the maximum value is 15F, which is equal to decimal 15, which can be represented using 4 bits in binary 1 1 1 1. So now for hexadecimal we will consider 4 bits, like how we consider 3 bits for octal. Integer part, that is left side of the decimal point, start from right to left, club 4 bits together, and if there are insufficient number of bits for the last combination, pad it with zeros. And for the fractional part, after the decimal point, start from left to right, group 4 digits together. Now each of these set of 4 bits, convert it into an equivalent hexadecimal number, and that gives you the solution. Similarly, converting a hexadecimal number to a binary number, consider each hexadecimal digit and represent it using 4 bits of a binary number, and there we have the binary equivalent of the hexadecimal number. Now for converting hexadecimal to octal or octal to hexadecimal, the normal procedure will be convert hexadecimal to decimal and decimal to octal, but instead we can convert hexadecimal to binary and binary to octal, which would be much easier. So hexadecimal to octal, the example given, the hexadecimal number is converted to a binary number representing each hexadecimal digit using 4 bits. Then convert this binary number to octadecimal by grouping 3 bits together, and we have the solution. Similarly, proceed from octal to hexadecimal. The given octal number is represented in binary and from binary to hexadecimal. So the problem that is given and the solutions are also given. Pause the video, complete and verify your answers. So in this video, we have seen the 4 important number systems: decimal, binary, hexadecimal and octal. We have also seen the conversion from any radix to decimal number and from a decimal number to any radix. And we have also seen for conversion for any radix to another radix, the radix 1 should be converted to decimal and then decimal to radix 2. Whereas for conversion from octal, hexadecimal and binary, a direct conversion method has been seen, a shortcut method has been used. These are the references used. Thank you.